Next talk will be given by Jack Verbaarschot. He will tell us about chaos on Hypercube. 45 minutes, please.
Okay, yeah, thank you. It is nice to be part of this workshop. Although online is a very different experience. One thing is that normal things don't work, so you still have to teach, etc. So my talk is about, in part, a new topic. It has Hypercube in the title instead of SYK. Otherwise, there's a lot of resemblance. So a hypercube is a cube in many dimensions in general, in d dimensions. Simplest cases in 2 dimensions, then you have 4 nodes. So this figure is drawn by Mathematica. It is in 8 dimensions. So each node is connected to 8 other nodes, and you can easily draw a picture yourself. The work was done in collaboration with my student, Yang Yia, who actually had the idea of looking at this. And the reason he got that idea was because there was a model by Giorgio Parisi. He had a hypercubic model for Josephson junctions. And in the large D expansion, there were some remarkable coincidences with the large N expansion of moments in the SYK model. That actually sparked our interest. And the second thing that sparked our interest was that the spectral density of the Hamiltonian associated with this hypercube is actually given by the density function of the Q-Hermite polynomials, and the same as it is for the SYK model in the double scaling limit that Q squared over N is fixed. So our paper will come out soon. It is basically finished, but it always takes some time to get the last points on the iota. I will start with reviewing the model, discuss the symmetries of the model, discuss the spectral density, the chaotic nature. In the last lecture, we heard about thermal field double states. They also there in this model, and I will end up with some conclusions. As I said, the model was invented by Giorgio Parisi in 2004, and it is a Laplacian in d dimensions, and the Laplacian, it is a discretized Laplacian on a d-dimensional cube, where in each dimension you have only 2 points. So the Hilbert space is 2 to the power d. And through all phases of the hypercube, there's a magnetic flux. The magnetic flux is constant, it's same through all phases. However, the orientation of the flux is taken at random. And the flux is realized by putting U1 gauge fields on the links, as you would, for example, do in lattice QCD. So as I said, this was a model for Josephson junctions. It is kind of an, I would say, an abstraction of, quite an abstraction of Josephson junctions. And I think the only remnant is that there's a phase which you have between 2 superconducting junctions. Okay, so let's look at the simplest case for the model that is in 2 dimensions. In 2 dimensions, the hypercube is a square. So there are 4 points, there are 4 nodes. These are the points of the hypercube. You can always choose a gauge in which some of the links, some of the phases on the links are equal to 1. And in this case, 1 has to be equal to -1. It is e to the power I phi. Phi is the times S21 is, S is the orientation, the random orientation. So if we calculate the Wilson loop around this given by e to the power S21. So the model is characterized by the fluxes of the Wilson loops. You can all ask questions during the lecture. So the Hamiltonian is given by, so for each point, so if you start from 0, there are 2 links of 1, so this is 0. There are 2 links of 1. If you start at 1, 0, that is this point. There is 1 phase to the 1, 1 point, and 1 to 0, that's that one, etc. And for the 1, 1 point, there's also 1 phase, but then you go in the other direction, and that is why there's a complex conjugation. So this is the 2x2 Hamiltonian. What you also see is that if the phase is equal to 0, then this is actually what is on the diagonal. That is the tensor product of 2 Pauli matrices with 1. That is this one. That is when phi is equal to 0. And what is on the off-diagonal matrix, that is, there are 2 identities when phi is equal to 0. So that's the tensor product of sigma 1 with 1. So, and then for phi equal to 0, this matrix is exactly the so-called adjacency matrix of the graph. And of course, that is an integrable system. When phi is not equal to 0, the system is no longer integrable. I already said that the Hilbert space is 2D dimensional, as many points as you have a lattice. So what you can do with the Hamiltonian, you can expand it in a Clifford algebra of gamma matrices in 2D dimensions. And then you can interpret it like a system of two-dimensional, 2D interacting in general, any two-body interaction terms, if you work it out, which we did, you get 2-body, 3-body, 4-body, 5-body, etc. interactions. Each point in the Hilbert space is connected to, in fact, d-1 other points. So the model reminds you of an SY, but it is less random. So there are only d/2 random orientations, as many as you have phases, while in the SYK model, you have n/q random matrix elements, at least when q is equal to 4. This is larger than d/2. So we will look at this model from our experience with SYK model and from the perspective of the SYK model. And I guess most of you know that the Hamiltonian of the SYK model is a Hamiltonian of in the simplest case, simplest non-trivial case, of 4 Majorana fermions coupled by a random interaction. And in general, there are n different Majorana fermions. So some of the questions we would like to find out, and that is also why we started looking at that. And that is that Paris already discovered that the spectral density of this model is given by the Q-Hermite polynomials, the density function of Q-Hermite polynomials. And that means that the density of eigenvalues has a tail which looks very familiar times the square root of E naught. And this is exactly the tail that corresponds to the Schwarzschild action. So this model may have a low energy theory Schwarzschild action. The second question we asked is whether this model is chaotic. And so my internet apparently is unstable. And this question was not studied before. We will look into that, and what we will look at is the spectral correlations, and if they are given by random matrix theory, according to the Boygas conjecture, the corresponding classical system must be chaotic. So you could wonder, what is the corresponding classical system? It could be a classical system of Majorana fermions, but we haven't really addressed that question. So we know that for phi equal to 0, the model is integrable. So what can we say about the onset of chaos? So let's now study the structure of the Hamiltonian and its symmetries. In this graph, you see a plot of the non-zero matrix elements of the Hamiltonian for 10 dimensions. So you clearly see a fractal structure. So if you take this Hamiltonian, if the next dimension is by putting 2 blocks of these, maybe I started this. If you take this Hamiltonian, next one is by taking 2 blocks, the same blocks, and then coupling them in this way. So the Hamiltonian can be determined recursively. In D dimensions given by 2d-1 blocks, coupled by a diagonal matrix. And the diagonal matrix is a matrix of the links that couple these 2 blocks. So it has a very simple fractal structure. It doesn't look chaotic at all, and of course that is a surprise. For phi equal to 0, the Hamiltonian is very simple. In D dimensions, it is a sum over exactly the same as in the 2-dimensional case, the sum of the tensor product of identity operators, 2 by 2 operators, then a sigma-1 matrix, and then again identity operators. And the sigma-1 can appear in any place. What you can do then is you can write each of these terms in terms of gamma matrices, because sigma-2 times sigma-3 is sigma-1. And we can call this the left gamma matrices. There are d of them, and these are the right gamma matrices. And then the Hamiltonian is given by the sum from k equal to 1 to d of gamma k right times gamma k left. And this is exactly the coupling term in the so-called Madasena Xi model. So we expect that this model also has the Madasena Xi model. If you look at the spectral flow, where here are plotted the eigenvalues, and this is for d equal to 8, as a function of the flux changes from 0 to pi. For zero flux, the system is integrable. The Hamiltonian is given by a sum of products of left and right gamma matrices. All these gamma matrices are different. That means each term, they all commute, these t terms commute with each other, which means that they can be diagonalized simultaneously. And they have the squares, of course, 1 of each of the terms. So the eigenvalues are of each term are plus or minus 1. And that means that the spectrum is given by minus d plus p, and the binomial factor d over p. And that is what you see. So the ground state is non-degenerate. Then the next state is d over 1. And I plotted 2 graphs because we will see in a minute that this model as the Malazena Xi model has a discrete symmetry, which we denote by the quantum number S, which is 1 here and minus 1 there. What we also see is there's a gap between the ground state and the rest of the spectrum. This gap does not vanish in the limit that T gets very large. For small flux, we just see a Zeeman splitting of all degenerate levels. And then at some point around here, this is the chaotic region. And while for flux phi larger than pi over 2, the spectrum splits into 2 bands. We don't really understand that. We understand it. We have some understanding of it. While for flux pi, the eigenvalues are exactly equal to plus or minus square root of dimensions, which you can, and the reason is that if you look at the trace of the square of the Hamiltonian, the Wilson loops, the 2 pairs corresponding to the Wilson loop exactly cancel. This spectral flow reminds you of the spectral flow of the Malazena Xi model. This for the same number of states. The left-hand side is identical. Oh, this gets blue. That's not a good thing. So the Malazena Xi model is a Hamiltonian with exactly the same coupling term, but the uncoupled Hamiltonian is different. It's a sum of the left and right Hamiltonian. There's Zeeman splitting, and in between the model is chaotic, and then it goes to the eigenvalue. Also, the Xi model ground state is separated from the rest in the thermodynamic limit, and it is actually a thermal field double state. And that is why for the hypercubic model, we also have studied if the ground state is given by a thermal field double state. This model has 2 symmetries. One symmetry is a chiral symmetry. The model is a bipartite lattice. So that means one lattice is coupled to the other lattice and not in between themselves. And you can define a gamma 5 operator that anti-commutes with the Hamiltonian. So gamma 5 is the tensor product of sigma 3 matrices, which is really the gamma 5 of the gamma 5 matrices. And this implies that all eigenvalues are paired plus or minus lambda. And you can also easily find a basis where the Hamiltonian explicitly has the chiral block structure. The second symmetry is actually much more subtle. It was actually not known to Parisi that this symmetry existed. The reason we found this symmetry was exactly the same reason as we found the symmetry in the Malazena Xi model, and that is we studied the chaotic properties of the levels of this model, and it turned out that half of the levels didn't have level repulsion. And that can only happen if there's a symmetry. In this case, the symmetry is a magnetic inversion because the magnetic field is invariant, changing the points xk to 1 minus xk. And in the lattice is, as in the two-dimensional case, is characterized by zeros and 1. So 0, 0, 0, 1, 1, 0, etc. And there's this inversion symmetry, which means that in terms of the Hamiltonian, that it commutes with an operator. This operator is actually to what you find with magnetic translations. It's the same kind of form. It's a tensor product of d operators, and each operator has some phase factor in the off-diagonal matrix element. And the phase factor is given by the sum of all orientations in d dimensions. Of course, the square of this this inversion, so AD squared is equal to 1, because each of the squares of KD is equal to 1. So that means that the spectrum splits into two pieces as flow. So let's now look at the spectral density. Are there any questions?
Sorry, could you please repeat the last sentence about the spectrum, because it cut out completely for me, at least.
You mean about the
Yes.
yeah. So the Hamiltonian commutes with this operator. The square of this operator is equal to 1, because the square of each of these 2 by 2 matrices is equal to 1. And that means that the spectrum splits into 2 parts, one with eigenvalues of A minus 1, and the other with eigenvalues equal to 1. So when we study eigenvalue correlations, we do it for each sector separately. Superposition of 2 entities. Any more questions? Okay, so let's now look at the spectral density. The spectral density is given by the Fourier transform of the characteristic function, and the characteristic function is determined by the moments. So if we know the moments, we in principle know the spectral density. For the hypercubic model, these moments are given by, it's a trace, it is given by the sum over all closed paths on the hypercube. And on a hypercube, you can have different closed paths. You can have paths that retrace themselves. And of course, those paths do not depend on the flux, because there's no flux through the path. And also paths with closed loops. And each closed loop gives a factor cosine phi from the Wilson loop. And because you have to sum over all paths, you also have to include the reverse path. So you actually get the cosine of phi for a closed loop. And I think I have here a picture for trace h to the 4th. So here there's an example of a closed loop. So in general, there's a loop in d dimensions. So A is one direction, one dimension, B is the other, and it has to be closed. So you have to have A, B, A, B. You can also look at that as a contraction diagram, as you would do in the SYK model. When you do a Gaussian integral, a Gaussian average, you sum over all possible contractions. And this would correspond to a crossed diagram. The result of this diagram is d times d minus 1 times cosine phi, because first you can choose d dimensions, then d minus 1, and the Wilson loop gives cosine phi. You can also have retracing paths. For example, this one, you go with this and then that. Then there's no cosine phi factor. The result is, of course, d times d minus 1. And this corresponds to the diagram, contraction diagram, a planar contraction diagram, AABB. There's also ABBA. Again, that's a planar diagram. And again, d minus 1. There's also one that doesn't have a direction. When you go back and forth twice in the same direction, factor d, it is 1 over d suppressed. It doesn't have a direct correspondence with the chord diagram. However, you can relate it to this diagram because the number will be the same. This is very much similar as you calculate moments in the SYK model. In the SYK model, which is given by the sum of random couplings times products of 4 gamma matrices, which square equal to 1. When you average, you do Gaussian average, all gamma alpha occur in pairs. And for the fourth moment, you have 4 different combinations. Exactly as in the previous figure, we have gamma alpha, gamma alpha, gamma beta, gamma beta. Of course, that is equal to 1. I included this normalization factor. Also, this combination is equal to 1. Combination corresponding to the Wilson loop, when you have gamma alpha, gamma beta, gamma alpha, gamma beta. And in this case, you have to commute beta with alpha, and it commutes or anti-commutes depending on the number of indices alpha and beta have in common. And if you count that, you find when there are p in common, there's a phase factor minus 1 to the p. So the common ones, they are q over p, and the not common is given by this binomial factor. And this factor we denote by eta. So it's clear that the difference between the spectral density of the SYK model and the hypercubic model is that the eta for the SYK model becomes cosine 5 for the hypercubic model. And if you make that substitution, you should find the spectral density of the hypercubic model. So let's see how it works. For the SYK model, the spectral density is given by the Q-Hermite form, which was first discovered by Erdos and Schroeder for a random spin model. It is kind of a deformed semicircle, and it is given by the double scaling limit of SYK model, Q squared over n fixed. This is a result for the SYK model. There are 2 curves in these figures. I used a thin line, and they are extremely close. This is for n equal to 32 and q equal to 4. Spectral density of numerical calculated eigenvalues. This was done by Igor Klebanov and co-workers. Again, there's very close agreement with this formula, where this eta is actually calculated for finite n and finite q. There's no fitting, just plug it in, and then you get this agreement. For the hypercubic model, you can calculate the moments. You can calculate the fourth moment, the sixth moment. And the fourth moment you use to define eta. That is what goes into the Q-Hermite density. The sixth moment, this should be a square, is then given by this formula. There are still 1 over d squared corrections. And if you then expand the density in Q-Hermite polynomial, the A2 and A4 terms are equal to 0. There's an A6 term which can be calculated analytically. There are in principle higher order terms from the higher order corrections. You can calculate them by fitting. They are very small. And there's an important difference with the SYK model. In the hypercubic model, the fourth moment and the sixth moment do not depend on the realization. They are disorder independent. The eighth moment is not. In SYK's model, the second moment, the fourth moment and the sixth moment, and also the second moment, they depend on the disorder realization. And that means that the spectrum has collective fluctuations which are mixed up with the correlations of the spectra. So let's compare it to the Q-Hermite result. So in this figure, this for 14 dimensions, the flux is taken about a little bit more than pi over 4. And in this figure, there's a fit to the 8th order one coefficient is fitted, that's the 8th order, to see how big it is, but it's very small. And you see that there's an excellent agreement between the numerical result, which is the black curve, and the analytical result, which is the Q-Hermite density, which is the red curve. So you can tune phi so that cosine phi, so that eta becomes equal to 0. That would be the semicircle limit. And indeed, because of 1/d corrections, you actually have to take cosine phi equal to 1/d minus 1. Then eta becomes equal to 0. And indeed, you see a nice semicircle. Okay, I'm again getting blue. I don't know. I have to go back and forth. Then take phi larger than pi over 2. In that case, eta actually becomes negative. And in terms of SYK model, this corresponds to the supercharge of the supersymmetric SYK model, which you find for odd Q. And you see that actually it doesn't work that well. This was also the case for the SYK model. The reason is of technical nature. The expansion coefficients have a 1 over the NQ factorial. And when Q is negative, the NQ factorial becomes very small, so that all corrections are higher order corrections are enhanced, which you see. However, close to pi, it is again quite well approximated by the Q-Hermite result, and when the spectral density becomes close to two delta peaks. So let's now go look at the chaotic properties. How I'm doing with time. Okay. The correlations of spectra of chaotic systems are strongly universal. It is possibly the strongest universality in physics. That's even said by Steve Shankar, who worked a lot on universality in phase transitions. We looked at it already many years ago, at the same time as the Boiras conjecture came out, when we looked at chaotic systems with only 3 degrees of freedom, 2 spaces and 1 momentum. Then you see a transition between order and chaos. We also looked at eigenvalues of the QCD Dirac operator, which have universal properties. For that, we had to extend the Dyson classification with 3 chiral ensembles, and found, and that has been tested in many different areas. This type of universality was explained in terms of effective Lagrangians and spontaneous symmetry breaking. So it's completely understood analytically how that works. So, and also for spectra of SYK model, they are correlated according to random theory, which we worked on earlier on, and as well as Kotler et al. So what we study is the correlation function of 2 spectral densities, the pair correlation function. The spectral density is sum of delta peaks, and the pair correlation is you average a pair, and there's 1 bracket drawn here, and you subtract the expectation value of each of them, so that you get a connected correlation function. We look at 2 observables. One is the number variance. Then you look at the variance of the number of eigenvalues in an interval delta E. which contains n eigenvalues on average. Another one is the spectral form factor. And the spectral form factor is simply the Fourier transform of the pair correlation function. We always use the connected form factor. Many people are not doing that, for example, but it's very important to do that when you compare to random matrix theory, when you make unbiased comparisons. It is also important to actually to calculate the spectral form factor. You have to unfold the spectrum. That means map the spectrum to a spectrum with average spacing equal to 1 everywhere. Otherwise, you don't have to do that for the number variance because you have this interval delta E. The number variance is related to the spectral form factor and can be obtained by just integrating this over the right integration kernel. So the two are one-to-one related. For the SYK model, what we see is that the number variance versus the number of intervals, it agrees very well with random matrix theory. In this case, the Gaussian unitary ensemble for a while, and then it starts deviating. These deviations are quite well understood now. Whereas the spectral form factor has this shape. This was obtained by Kottel et al. And so it has a flat piece here that corresponds to the linear part here. Then is what these people call the ramp. The ramp is this piece. And this peak is not in this figure. This is the disconnected part of the correlation function. It is huge, and we always subtract that. And if you subtract that, which I did here, it goes away completely, and you find agreement with random matrix theory up to very small times and very small values. In the previous figure, this went all the way up to the ceiling. And also, the other thing what we did is, I said we understand the deviations from random matrix theory. The deviations are because of collective fluctuations from one realization to the next. But if you subtract them, you find agreement up to very large distances, up to 2000 in this case, and even higher, and up to very short times. So let's now look at the hypercubic model, where we plot here the number variance for different values of the magnetic flux and 14 dimensions all. And you see a very similar figure than the SYK model. It follows the random matrix behavior up to some distance, and then it goes away. For the hypercubic model, you don't have these collective fluctuations. So that means that actually for large n, it actually, the deviation is much less than in the SYK model. This is the same figure, but then for all the way up to 1000. This is at the semicircle case. The deviation becomes larger. I think also because there's a transition to two bands, and at large distance you see a larger deviation. Also in the two-band case, there's still good agreement with random matrix theory. If you look at the, okay, still 5 minutes. If you look at the spectral form factor, you actually see excellent agreement. So this is the Gaussian unitary ensemble. And if you have good classes, not only good eyes, but also good classes, you actually see a tiny little peak down here. Tiny, about 0.02. And this tiny little peak is responsible for the deviation in the number variance. If you magnify this area, you actually see this peak. So all the deviations is localized at small times. For the semicircle case, that's this case, the peak near zero goes all the way up to 1.1. And you magnify that here. And of course, that gives much larger deviations. And finally, here you find again smaller deviations. So this beautifully confirms the chaotic nature of the spectra of the hypercubic model. There's something new in the hypercubic model. It has a chiral symmetry. And because of the chiral symmetry, eigenvalues come in pairs, and this introduces correlations between the eigenvalues. They can be measured by the microscopic spectral density, where you look at the spectral density on the scale of 1 over the volume. That's the dimension of the Hilbert space. And there's an equal sign here. Sigma is roughly the level density near zero, that is this. And then you see these oscillations. These oscillations are, this is the position of the first eigenvalue, second, third. You can obtain them analytically in chiral random matrix theory. It's given by this expression in terms of Bessel functions. And you see that it indeed agrees very well. So there's no fitting going on for this figure. And we first looked at this in the context of QCD in these papers, where we also introduced the chiral random matrix theories. In the last couple of minutes, I will discuss the thermal field double state. For the model CNRG model, you had a tensor product of a left Hamiltonian with one and a right Hamiltonian, which were coupled by coupling terms of gamma matrices. And for this model, you can calculate the ground state. And the ground state is very close to a thermal field double state. That means a state of states M, which are eigenstates of say the left Hamiltonian, or maybe the right Hamiltonian here. And these are the charge conjugate states of eigenstates of the left Hamiltonian. And this is a thermal factor. So this gives a good approximation to the ground state. Here there's a logarithmic plot. The thermal factor for the expansion coefficients of the ground state would be the red curve. So you actually see pretty large deviations from the TFD state. So let's look how this works for the hypercubic model. For the hypercubic model, at zero flux, we again have a Hamiltonian, I forgot an I here, which is the product over left and right gamma matrices. And this goes to n over 2 is equal to d. Then you can use these gamma matrices to construct SYK models. So that there's a right SYK model times 1 and a left SYK model, which then is given by the sum of interaction coefficients, which are random, times here there are the right gamma matrices, here are the left gamma matrices. And then it turns out that for phi equal to 0, the ground state of the hypercubic model, that's this model, is exactly a thermal field double state. It is the sum over e to the power beta em over 2 times m times minus m. M is the eigenstates of this and minus m of this. So in this case, it are actually the zero energy states of HR plus HL. So this is because this model has a chiral symmetry, and the temperature actually is infinite. There's no temperature dependence for phi equal to 0, which is also the case for the model CNRG model at infinite coupling. However, in this case, at all couplings, the temperature is infinite. And here you see the overlap of the ground state with the states that occur in the thermal field double, m minus n. For phi equal to 0, this gives you the full strength of interaction. For small phi, it works still pretty well, but at larger phi, quite a bit of the strength goes through the other part of the space. But the states are very close to a thermal field double state. Here are the energies of one of the two-body Hamiltonian. One remark I also should say is that the thermal field double property actually is independent of the choice of the Hamiltonian that determines the basis. We could also have chosen here a four-body SYK model, and we would have also have found that the ground state of the hypercubic model for phi equal to 0 would have been a thermal field double, but we didn't try that. How am I doing with time? Okay, so let me conclude. So what we have seen is that a hypercubic model is well described by a spectral density that is QM-neat. So it has a sign hyperbolic square root of E minus E naught tail. The model is chaotic. The eigenvalues are correlated as the Caro-Gaussian unitary ensemble. Its dynamics must also be chaotic for not too small values of the magnetic flux. We have seen that the ground state is separated from the rest of the spectrum by a gap. This has important implications for the phase diagram of the theory. We haven't looked at that, but Parisi did many years ago. He looked at it numerically, but I'm sure we can make more progress to understand the phase diagram better. So one of the questions we have is what is the low energy limit of this model in order to better understand the chaotic nature of the spectra. Also the phase diagram, but I also already mentioned that. So that's all. Thanks for your interest.
Okay, thank you very much for your very interesting talk. Any questions, please? If no, maybe I will ask some technical problem, maybe I missed something. You just shown us this sign formula with square root, and there is a parameter E0. And how you define this E0 from original hypercubic model? Maybe where was formula, maybe I missed it.
Yeah, E0 is actually directly related to, I have somewhere a formula, it's directly related to the variance of the hypercubic model. The trace h square sets the scale. You can calculate that analytically, as you can for the SYK model. And then this is E0. So the variance is the overall scale. This would, for the SYK model, this would also be the variance of the Hamiltonian. The sigma squared is trace h squared. And then there's a factor, square root of 1 minus eta. This eta would be cosine phi for the hypercubic model. For you might say for phi equal to 0, it becomes 1. And then E0 is actually infinite. And actually that is right, because at phi equal to 0, the spectrum is discrete. It is a binomial spectrum, but actually it is a Gaussian because a binomial is a Gaussian in some limit. So in a large n limit, the spectrum goes between minus n and n, so that it becomes large. So, but this defines the E naught uniquely. You calculate it, and it agrees with what you find numerically.
Okay, thank you. More questions, please?
I would like to ask a question. Jack, could you please show the slides when you plot the number variance for different cases for the hypercubic model?
Yeah. Oh. This one.
Yes, yes. So on the last picture, there seems to be like the same fluctuations which grows with the x-axis. Why is this happening? Yeah. So
you mean these little peaks?
Yeah.
Yeah. These little peaks happen because what we do is we add to statistics. We average the interval delta E over the spectrum. And when n becomes large, there are only a small number of different intervals, like 5 or 3 at these values of n. And you get a little peak when you change from 3 to 4, because the reason is that what you measure are deviations from the analytic form of the spectral density. And they are correlated because the thing is normalized. So if you undershoot in the tail, you overshoot in the middle. And if you have only 3 intervals fitting in the spectrum, it makes a very big difference if you have 3 or 4, because with 3 you would get the bulk and not come very far in the tail. And with 4 you see much more of the tail, and that gives you these discrete peaks. So these are just finite size effects, and they always occur when you have only a very small number of intervals to average over. Not only in this system, but in any other system. You also see that here. This is the same effect.
But in that plot, it's actually, well, it looks different to me.
They occur differently. It also depends on exactly how you do that. Here, actually, they were very, very large to start with, but then I had to basically chop off. So what you can do is you can choose the starting interval differently. If you start, because you have to start somewhere calculating, but you can start, for example, at a random point instead of at a fixed point, so that each time you have slightly different summing, averaging over intervals, and that actually gives fewer fluctuations. So we try to deal with that, but you cannot really, because this is a real effect. It's a real finite size effect, and you cannot really eliminate that.
Okay, I have also another question. So Douglas Stanford in his talk discussed quantum JT graded finite cutoff and his typical quantum configurations of the boundary representation modes were some fractal curves, essentially, the non-self-attracting random walks. And in the model that you study, you have this is a super naive question, by the way. You have a Hamiltonian with a fractal structure. Do you think there could be some relation between this model as a boundary dual for the quantum graded finite cutoff?
Yeah, I would like to see some relation. I don't know it. Of course, it is intriguing that you have a relation between geometry and chaos. You have a very nice geometric model. It still turns out to be chaotic. It is also fractal in some sense, but I cannot make any more precise relations. It would be nice to do that, but it's very interesting.
Okay, thanks.
Please, more questions? Okay, it seems there is no more question. Let's thank Jack once again. Thank you very much.
Thank you.
Thank you very much. Very interesting.